Imagine a world where no one is in charge. No central bank, no government ledger, no authority you can call when something goes wrong. Now imagine that in this world, strangers who will never meet each other are somehow able to agree on who owns what, who paid whom, and which transactions are real, all without trusting a single person. At first glance, this sounds impossible. Human history tells us that money has always relied on trust. Gold required trust in its purity. Paper money required trust in the institution printing it. Digital money required trust in banks, servers, and intermediaries who promised to keep honest records on our behalf. Remove that trust, and the entire system collapses. This was the core problem Bitcoin set out to solve. Before Bitcoin, digital money had a fatal flaw known as the double spending problem. If money is just information, what stops someone from copying it and spending it twice? The traditional answer was simple. You appoint a trusted third party. A bank keeps the ledger. A payment processor verifies balances. A central authority decides which transaction is valid and which is not. But what if that authority lies? What if it makes a mistake? What if it is coerced, corrupted, or simply prints more money when it benefits those in power? Bitcoin begins with a radical assumption: trust no one. Instead of asking, who should we trust to tell the truth? Bitcoin asks a far more uncomfortable question. How do we make lying so expensive that telling the truth becomes the rational choice? This is where proof of work enters the story. Contrary to popular belief, proof of work was not invented to create new Bitcoins. It was invented to create truth in a hostile environment. An environment where anyone can participate, anyone can attempt to cheat, and no one has special privileges. To understand why proof of work matters, we need to understand what Bitcoin is really protecting. Bitcoin is not protecting coins. It is protecting history. Every Bitcoin transaction becomes part of a shared historical record called the blockchain. This record answers one fundamental question over and over again. What happened first? Who owned these coins before? And who owns them now? If someone can rewrite that history, they can steal. They can reverse payments. They can erase transactions they don't like. In traditional systems, rewriting history is frighteningly easy. Change a database, adjust a spreadsheet, issue a correction. The power to edit the past is concentrated in the hands of a few. Bitcoin flips this entirely. In Bitcoin, history is not protected by authority. It is protected by cost. Proof of work turns the creation of history into a physical process, not physical in the sense of paper or ink, but physical in the sense of energy, time, and computation. To add a new page to Bitcoin's history, you must prove that you have expended real-world resources. Electricity was burned, hardware was used, time passed that cannot be undone. This changes everything, because now, making a claim is cheap, but proving it is expensive. Anyone can say, this transaction is valid, but only someone who has performed the work can make that claim stick. This design choice reflects a deep understanding of human incentives. In an open system, you cannot rely on honesty. You cannot rely on goodwill, but you can rely on self-interest, if the rules are designed correctly. Proof of work aligns self-interest with truth. Miners, the participants who perform proof of work, are not trusted because they are good people. They are trusted because cheating costs them money. If they try to include invalid transactions, the rest of the network will simply reject their work. All that energy, all that computation, wasted. No reward, no recognition, just loss. This is a brutal system, and that is precisely the point. Bitcoin does not ask participants to behave morally. It asks them to behave rationally. And rational actors, when faced with high costs and low rewards for cheating, tend to follow the rules. Another crucial idea emerges here. Bitcoin does not prevent attacks by hiding information. Everything is public. The rules are transparent. The code is open. Anyone can attempt to break it. Security does not come from secrecy. It comes from asymmetry. Doing the work is hard. Verifying the work is easy. This asymmetry is the foundation of proof of work. It allows millions of independent participants to quickly agree on what is valid without ever having to trust each other. A node does not need to know who you are, where you live, or what your intentions might be. It only needs to verify one thing. Did you actually do the work? If the answer is yes, the block is accepted. If the answer is no, it is ignored. No debate, no voting, no negotiation, just math, energy, and time. As we move deeper into how proof of work actually functions, it's important to keep this perspective in mind. Proof of work is not a technical trick, it is a philosophy encoded into software. A worldview that assumes conflict, dishonesty, and competition, and then uses those very forces to create order. The real question is no longer whether someone might want to cheat Bitcoin. Of course they do. The real question is this: how much are they willing to pay to do it? And that question leads us directly into the machinery of proof of work itself. Once you understand that proof of work exists to protect history, not to mint coins, the mechanics start to make sense. What looks chaotic on the surface is actually a carefully engineered process designed to turn raw energy into agreement. At the center of this process is the block. A block is simply a container for recent transactions, bundled together and prepared to be added to Bitcoin's shared history. But a block is not considered real just because someone says it exists. It only becomes real when the network accepts it. And the network accepts it only when the creator of that block proves they have done the work. That proof takes the form of a cryptographic puzzle. Every block has a unique fingerprint called a hash. A hash is produced by running block data through a mathematical function that spits out a string of seemingly random characters. The critical property of this function is that it is unpredictable. You cannot reverse it. You cannot shortcut it. The only way to get a desired result is to keep trying again and again. Miners take the block data, slightly modify one tiny piece of it, and compute the hash. If the resulting hash does not meet the network's difficulty requirement, they try again, and again, and again, trillions of times. This is where the work in proof of work comes from. There is no clever trick, no hidden insight, no optimization that lets someone skip ahead. The process is intentionally dumb, blind trial and error. The only advantage comes from expending more energy and running more machines. What the network demands is not just any hash, but a hash that falls below a specific target. This target is what makes the puzzle hard. The lower the target, the fewer valid hashes exist, and the more attempts are required to find one. The difficulty is adjusted automatically so that, on average, the entire global network finds one valid block roughly every 10 minutes. This timing is not accidental. 10 minutes is slow enough that blocks propagate across the world before the next one is found, but fast enough to keep the system responsive. It creates a steady heartbeat for Bitcoin, a rhythm that cannot be rushed without adding more energy. And here's the key insight. When a miner finally finds a valid hash, everyone else can instantly verify it. Verification takes milliseconds. A regular laptop can do it. The network doesn't need to trust the miner's word. It simply runs the same calculation and checks the result. Either the hash meets the requirement or it doesn't. There is no ambiguity. This asymmetry, expensive to produce, cheap to verify, is what allows Bitcoin to scale trust without centralization. When a valid block is broadcast to the network, nodes check several things. Are the transactions valid? Do the inputs exist? Is the block formatted correctly? And crucially, does the hash satisfy the proof of work requirement? If the answer to any of these questions is no, the block is discarded. It doesn't matter how much energy was spent. Invalid work is still invalid. This creates an unforgiving environment. Miners are constantly competing, but they are also cooperating, whether they realize it or not. By following the rules, they help extend the same shared history. By breaking the rules, they isolate themselves and waste resources. One subtle but important point is that miners are not choosing which version of history they like. They are choosing which version of history has the most work behind it. Bitcoin does not care about opinions. It does not care about intentions. It only measures accumulated energy. The chain that survives is not the one declared correct by a committee, but the one that represents the greatest total amount of computational effort. This is why the phrase longest chain is misleading. It's not about length in blocks, but weight in work. Every new block reinforces the blocks before it. Once a block is buried under many layers of additional work, reversing it becomes exponentially harder. You're not just redoing one puzzle. You're racing against the entire network in real time while recreating all the work that came before. And all of this happens automatically. No one schedules the miners. No one assigns tasks. No central server tells them what to do. They simply respond to incentives. Valid work is rewarded. Invalid work is ignored. Even the reward itself is secondary to the process. Yes, miners receive newly issued Bitcoin and transaction fees, but that reward is not the point. It is the fuel that keeps the engine running. The real output of mining is not coins, it is consensus. Proof of work transforms energy into agreement. Electricity flows through machines. Machines perform meaningless computations, and out the other side comes something deeply meaningful, a shared, tamper resistant timeline of events. As strange as it sounds, the randomness of the process is a feature, not a bug. Because no one can predict who will find the next block, no one can reliably control the system. Power is constantly redistributed. Leadership rotates every 10 minutes, chosen by math, not by influence. By the time a block is accepted, it is already old news. The network has moved on. Miners are already working on the next one, stacking fresh layers of work onto the past. And this is where proof of work reveals its deeper purpose. It doesn't just decide what happens next, it locks in what already happened. To change the present, you must first rewrite the past. And rewriting the past requires an extraordinary amount of work. That realization takes us to the real strength of proof of work: security, irreversibility, and the economics of attack. At some point, every serious discussion about Bitcoin arrives at the same question. If everything is open, public, and permissionless, what stops someone from simply taking over? What prevents a powerful actor, a corporation, or even a nation state from rewriting the ledger and bending the system to their will? The answer is not that attacks are impossible. The answer is that attacks are irrational. Proof of work does not promise perfect safety. What it promises is something far more realistic. It makes dishonesty brutally expensive, continuous, and visible. To understand this, we need to look at what an attack actually means in Bitcoin. In traditional systems, attacking history is surprisingly easy. You pressure a database administrator, you alter a record, you issue a rollback. Control the institution, and you control the past. The cost is primarily political or organizational, not physical. In Bitcoin, history is layered. Each block is built on top of the one before it, and each layer represents real-world energy that has already been spent. Once a transaction is confirmed, it becomes part of a block. Once more blocks are added, that transaction is buried under increasing amounts of proof of work. Time and energy harden it into place. To change a past transaction, an attacker must do far more than modify a file. They must recreate the block containing that transaction and then rebuild every block that came after it. And they must do this faster than the honest network continues to extend the legitimate chain. This is where the economics become unforgiving. Bitcoin's consensus rule is simple. The valid chain with the most accumulated work wins. Not the chain declared by the loudest voice. Not the chain preferred by the richest users. The chain backed by the greatest expenditure of energy. An attacker, therefore, must outspend the rest of the world combined. This is often described as a 51% attack, but the name can be misleading. It's not a one-time threshold you cross and then win forever. It is a relentless race. For as long as the attack continues, the attacker must maintain more computational power than everyone else. Not yesterday, not once, but continuously. The moment they fall behind, their alternative history collapses. And here's the critical part. Even if an attacker succeeds, their power is limited. They cannot create Bitcoin out of thin air. They cannot steal coins without owning the private keys. They cannot break cryptography. The only thing they can realistically do is attempt to reorganize recent history, typically to reverse their own transactions. Even then, the cost is staggering. Energy must be purchased, hardware must be acquired, infrastructure must be built. And all of this investment produces no lasting advantage unless the attacker keeps spending. The attack itself does not grant permanent control. It only rents influence at enormous cost. Meanwhile, the honest network keeps operating. Miners around the world continue to add blocks, stacking more work onto the legitimate chain. The deeper a transaction is buried, the more absurd it becomes to challenge it. This is why Bitcoin does not offer instant finality. It offers probabilistic finality. Each new block reduces the probability of reversal, not by social agreement, but by mathematics and economics. 6 confirmations is not a magic number. It is a practical recognition that beyond a certain depth, the cost of rewriting history exceeds any plausible reward. Another often overlooked aspect of proof of work security is that attacks are public. There is no stealth mode. Attempting to rewrite the chain is immediately visible to the entire network. Exchanges can pause. Nodes can wait for more confirmations. Markets can react. Contrast this with traditional systems, where fraud is often discovered long after the damage is done. Bitcoin's security is not based on secrecy. It is based on exposure. And exposure matters because it allows rational actors to respond. It allows users to adapt behavior in real time. The system bends, but it does not break. Perhaps the most profound aspect of proof of work security is that it ties digital truth to the physical world. Electricity grids, semiconductor supply chains, geographical distribution. These are not abstractions. They are constraints imposed by reality itself. To attack Bitcoin, you are no longer fighting software. You are fighting physics, logistics, and global competition for energy. And unlike centralized systems, there is no single point of failure, no headquarters to seize, no CEO to arrest, no server to shut down. Power is fragmented across countless independent operators, each acting in their own self-interest, yet collectively reinforcing the same system. This is an inversion of traditional security models. Instead of defending a castle, Bitcoin creates a battlefield where attackers must expose themselves and pay continuously. Even more interesting is the fact that miners are economically disincentivized from destroying the system they depend on. The hardware they own, the Bitcoin they earn, and the ecosystem they rely on all lose value if trust collapses. Rational attackers quickly realize that attacking Bitcoin is often less profitable than participating honestly. Proof of work doesn't rely on goodwill. It relies on game theory. It assumes that people will act in their own interest, and then it structures the system so that protecting the network is the most profitable strategy available. Bitcoin does not eliminate power struggles. It reframes them. Instead of backroom deals and political maneuvering, conflict plays out in the open, governed by energy and cost. There are no shortcuts, no appeals, no exceptions. The past becomes heavier with every passing block. And at a certain point, the weight of history becomes too heavy to lift. That is the real security of proof of work. By the time you understand how proof of work secures Bitcoin, a deeper question naturally arises. If this system consumes real energy, competes for real resources, and deliberately makes computation expensive, is it worth it? And more importantly, what exactly is being protected that justifies such cost? Critics often frame proof of work as wasteful. They focus on the electricity consumed, the machines humming in vast warehouses, the raw scale of computation devoted to what appears at first glance to be meaningless math. But this criticism only makes sense if you ignore what proof of work replaces. Every society pays an energy cost to protect its system of trust. Banks operate data centers, office towers, and global networks of servers. Armored vehicles move cash. Courts, regulators, and auditors enforce financial rules. Militaries ultimately stand behind national currencies, whether acknowledged or not. These systems consume energy, labor, and political capital on a massive scale, yet their costs are rarely questioned in isolation. Proof of work does something radical. It compresses the cost of trust into a single transparent metric: energy. Instead of trusting institutions, you trust physics. Instead of trusting promises, you trust expenditure. Instead of trusting people, you trust incentives. Bitcoin's proof of work anchors digital value to the physical world. You cannot vote more Bitcoin into existence. You cannot negotiate your way into rewriting history. Every block carries the unmistakable signature of energy already spent and time already passed. This is why proof of work feels uncomfortable. It removes flexibility. It removes discretion. It removes the ability to fix things after the fact. In exchange, it offers something rare in modern systems: predictability. No one can wake up tomorrow and decide that the rules have changed for their own benefit. This rigidity is often mistaken for a flaw. In reality, it is the feature that makes Bitcoin different from every monetary system before it. Proof of work enforces discipline not through authority, but through cost. There is also a philosophical dimension that is easy to miss. Proof of work assumes that humans are not angels. It does not ask participants to be fair, ethical, or altruistic. It simply assumes they will act in their own self-interest. And then it uses that self-interest to secure a global system. Miners do not need to care about Bitcoin's ideals. They do not need to believe in decentralization or sound money. They only need to want the reward. And in chasing that reward, they reinforce the integrity of the system for everyone else. This alignment is rare. Many systems fail because they rely on good intentions. Proof of work succeeds because it assumes the opposite. It channels greed, competition, and ambition into something productive, not by suppressing human nature, but by harnessing it. There is also the question of alternatives. Other consensus mechanisms promise efficiency, speed, or reduced energy consumption. Some of them achieve these goals by reintroducing trust, privilege, or central points of control. They may work for certain use cases, but they answer a different question. Bitcoin's question was never, what is the fastest way to agree? It was, what is the hardest history to fake? Proof of work answers that question by making history expensive, and that expense has consequences beyond technology. It creates a form of money that is politically neutral, no borders, no citizenship requirements, no permission. Participation is open to anyone with access to energy and hardware. In this sense, proof of work is not just a security mechanism. It is a statement about fairness. The rules apply equally to everyone. There are no shortcuts for the powerful. Influence cannot override math. Bitcoin does not care who you are. It only cares what you can prove. This has profound implications in a world where trust in institutions is fragile and increasingly polarized. Proof of work offers a system where agreement does not depend on shared values or shared beliefs. It depends on shared verification. You don't need to trust the miner. You don't need to trust the developer. You don't even need to trust the majority. You only need to trust the rules and your ability to verify them. And perhaps that is the most radical idea of all. Proof of work does not promise a perfect world. It does not eliminate conflict, inequality, or power struggles. What it offers is something simpler and more honest. A system where power has a measurable cost, where history resists manipulation, and where truth emerges not from authority, but from effort. Bitcoin doesn't ask humanity to be better. It asks us to be exactly who we already are. And then it builds a system that works anyway.